Solving a linear system of equations is an important problem in many fields of science. However, the general algorithm to do this, namely Gauss-Jordan elimination, is not an efficient algorithm. So people are always on the lookout for special types of systems that might be solved for using some more efficient technique. We have already seen one such method. If the matrix is sparse and diagonally dominant, in that case the Gauss-Jacobi method or its variant Gauss-Seidel method might be used. Now today we shall discuss another such special type of matrix. In order to set the stage, we will start with a very simple type of matrix that you can solve very easily. That is, if the coefficient matrix is of that special type, you can solve it very easily just by hand. And these are triangular matrices. Let's take the example of a lower triangular coefficient matrix like this. If I ask you to solve this system, then you can do it very trivially because look at the first equation, it involves only x. Here we have only zeros. So this equation is simply x equal to 9. Nothing to solve basically. Once you know x, now look at the second equation which involves only x and y, which is 2x plus 3y equal to 10. You already know what x is, so you can immediately solve for y. Once you know x and y, now look at the third equation which involves x, y, you know them, and z. So z is the only thing that you need to solve for. In this way, you can start with x, then get y, and then get z. That is called forward substitution. A very similar technique works for upper triangular matrices also. Here we shall employ just the same thing in reverse order, namely backward substitution. Let's look at this example. Here the last equation involves only z, so you can immediately see that from 6z is equal to 11, you get z equal to 11 by 6. Now you look at the second equation, you are going backwards. That involves only y and z. Z you already know, so you take this on the right hand side and y remains the only unknown. Once you know y and z, you go back to the first equation and solve for x. Unfortunately, not all matrices are lower triangular or upper triangular. However, there is a broader class of matrices for which the same idea of forward substitution and backward substitution works. These are matrices that may be constructed by multiplying lower triangular and upper triangular matrices. Suppose I have a matrix which can be factorized as L times U, where L is a lower triangular matrix and U is an upper triangular matrix. Then we can solve a system with this A as the coefficient matrix by using forward substitution and backward substitution both. Here is such a system where the coefficient matrix is the product of one lower triangular matrix and one upper triangular matrix. This is any right hand side. If I want to solve a system like this, I will do it in two steps. In the first step, I will consider this entire thing as my unknown. Suppose I call this thing x prime, y prime, z prime. This prime does not denote transpose here. So now the system is just like a lower triangular system which I can solve using forward substitution. So in this case I can easily see that my x transpose will be 2 from this, and then I can solve for y transpose from the second equation, which is 2x prime plus 3y prime equal to minus 1. So from this I will get y prime equal to 1/3 minus 1 minus 2 into x prime, that will be 4. So minus 5/3. And similarly I can solve for z prime. So once I get these things, now I will focus my attention on this part of the system. So I will have 5, 2, 1, 1, 9, 2. Then my original unknowns, and that is equal to x prime, y prime, z prime. These are now of course known numbers to me. So I do not write x prime, actually I write 2. Then I write minus 5/3. Then I write whatever number I have. Once I get this, it is again a simple system of equations where the coefficient matrix is upper triangular. So I will start by working backwards, back substitution. So z will be half of z prime and I will work my way up. Thus, for matrices that may be written as L times U, we can solve the system pretty easily. The question is, how do I know, given a particular coefficient matrix, that it might be factorized as L times U, whether such a factorization exists or not? And secondly, even if such a factorization exists, how do I find one? And then there is the natural question, if it exists, will it be unique? We are going to see this with an example. Suppose that someone has given us this 4x4 matrix and we want to see if we can indeed factorize it as a lower triangular matrix times an upper triangular matrix. I do not know what the entries of the lower triangular matrix is, so I have just put dots. Similarly for the upper triangular matrix, except that I have put in the diagonal entries all 1. We shall see pretty soon that if such a decomposition exists, then you can always assume without loss of generality that these diagonal entries will be 1. We are going to see that in a moment. But a priori, we do not know whether such a factorization exists. In order to see whether such a factorization exists and to find one such factorization, if one exists, we start by just assuming, let's suppose that such a thing exists and try to find it. If you get stuck at some point, that will immediately show that such a factorization does not exist. So I need to get suitable numbers in place of these dots such that the product will give me this. That might look like a very complicated thing, but it is not. Just start carefully. Look at this first row. You see all these things are 0. The only possibly non-zero thing will be here. In this case, you have 1, 0, 0, 0. So if I multiply this row with this column, I am going to get this 1/1th entry. So it must be, if I call it x, then it must be x times 1 plus 0, 0, etc. will be this 10. So this number has to be 10. So I immediately know that this number has to be 10. Very similar argument will work in this case also. Multiply this row with this column. Thanks to all the zeros here, only the first entry will contribute anything to the final result, and that must be equal to 4. So whatever number we have here, that times 1 must be 4. Everything else will contribute only zeros. It does not matter what you have to write here because it will get multiplied with that 0. So this has to be 4. Same way, if I consider this times 1 must give me this. So that should be 2, and you already get the idea. I am basically copying this column into my L. So this has to be 2. So So this is my L matrix and that is my U matrix. So the first column here must be the first column of L. If LU decomposition has to exist, L must have this as the first column. I assume that this is equal to 1. Now you might think, what if this is not 1 but this is 2? Well, if this is 2, nothing changes actually. You will replace this by their halves. That's all. What happens if it is 100? I will replace these things by 100. What happens if it is 0? That cannot be. If it is 0, then this thing must be all zeros. But I can see they are not zeros. So this cannot be 0. It has to be something non-zero. If it is something non-zero, without loss of generality, you make it 1, because if you make it anything else, then you just scale it appropriately. This also shows LU decomposition, if it exists, cannot be unique. Because you can multiply 1 with 100 and divide the other by 100. Still, since you have multiplied just by a scalar, both of them will retain their triangular character, but change. But the values will change. Okay, now let's attack these numbers. So I have found out the first column of L. Let's try to find out the first row of U. A very similar technique. In this case, I will now take, now that I know this is 10 times this number plus, thanks to this being zeros, they will not contribute anything. So 10 times this number must be 30. So this has to be 3. Do you understand this? Let's do it again for this column. This row times this column will give me this 30. These are all zeros, so these 3 will not contribute anything. 10 times this must be 30 again, so it has to be 3. You get the pattern. I am basically taking these numbers and dividing them by this 10, which is effectively this 10, and writing it down. So 10 by 10, this should be 1. So I got the first column of L. Now I have got the first row of U. Now I will come back to L. I will try to find these 3 numbers. Let's see how I do it. Excuse me. So what I will do is I will take this row and this column and multiply them out. These things being 0, I will have 4 times 3. Let me write it down. 4 times 3. The quantity that I am trying to find out, call it x, plus x times 1. I do not care what is after that because I have 0 here. That must be this 20th entry, 22. That will tell me that x must be 10. So I know I have a 10 here. Similar technique will give you this. So let's try out this one. I will always be working with this second column. This times the second column. 2 times 3. Then the quantity that I am trying to find out, again I will call it x. X times, well, it is again the same one. You will always get x times 1 equal to, now I will get this 15. So x will be now 9. So this is 9. Very similar pattern will work here also. It will be 2 times 3 plus x times 1 will be equal to 16. So that will be 10 again. So I get this. Once you have this, you can similarly fill these in. Now you will take the second row and multiply this with this. Because of these zeros, the only unknown will remain here this one and here this one. So you will be able to find out these numbers. After that, excuse me, after that you will come back to L and find out this. Then you will find this and then you will find this. So you can find all these things just by carefully looking at these entries in a particular order. From this, you might get the idea that LU decomposition always exists. Whenever anyone gives you a square matrix, you just keep on finding the various entries of L and U in this recursive way. But no, this procedure involves division at places. So things might go wrong. You might find that the denominator is 0. Let's take one such example. Suppose we want to find out LU decomposition for this square matrix. So I again proceed just the way we did earlier. So the first column here was just a copy of the first column there. Same argument will work here also. So the first column of L is easy to fill up, 0, 3, 6. Now I will try to fill up the first row of U. So how did I do that? I will consider 0 times 0 plus 1 times 1, 1 times this. Sorry, I made a mistake. I am multiplying these two. So 0 times this quantity plus 0 times this plus 0 times this. I am trying to find this element. So it is this row times this column, which is 0 times x plus 0 times 1 plus 0 times 0, and that is equal to 1. Oops, that cannot be. This is just 0 and this is 1. So had there been something non-zero, I would take everything on this side and divide by that number. But if I try to do that, I will basically get 1 minus 0 times 1 minus, these are all products, 0 times 0 divided by 0, and that is something very bad. In this case, actually, LU decomposition does not exist, and this itself is the proof. So you will say, let if possible LU decomposition exists. In that case, the first column of L has to be this. Then this number will become undefined. No number, no real number x will satisfy this relationship. So LU decomposition does not exist. Now you can construct more non-trivial examples where also LU decomposition will not exist, where this leading thing is not 0. You understand? This 0 is causing all the trouble. It's an interesting question to characterize all matrices that admit an LU factorization. Now, of course, if you want to check whether a given matrix has an LU factorization, then just carry out this algorithm and see if you get stuck. If you have to do some kind of division by 0, you have to divide a non-zero quantity by 0. In that case, you will immediately know that there is no LU decomposition. But can you come up with a mathematical description of all such matrices in terms of familiar concepts like determinant, rank, eigenvalue, etc.? It turns out there is an elegant answer to this question. Computationally, it does not help much, but the elegant answer is, if you look at all the leading principal submatrices, that is the top entry, then the 2 by 2 submatrix sitting at the top left hand corner, then the 3 by 3 submatrix sitting at the top left hand corner, and so on, all these square matrices must have non-zero determinant for, or if they all have non-zero determinants, then LU decomposition will exist. And this is not a necessary and sufficient condition. For example, if my original matrix is just the 0 matrix, that obviously has LU decomposition. You just take L to be the 0 matrix. But it is basically necessary and sufficient except for such borderline cases. So you can think about it. And the class web page will give you some hints about coming up with the mathematical characterizations of all matrices with LU decomposition. The algorithm that we mentioned about finding an LU decomposition if one exists turns out to be a very simple one, and also it may be implemented quite efficiently without using any additional memory other than the amount of memory that is being already used to store the original matrix. When we compute LU decomposition of a square matrix A, then we proceeded in the following way. We first took the first column of A, that is this, and then just copied it here. And then we computed these things using the remaining part of the first row of A. In other words, we used this part to compute this part of U. Now, what you may not have noticed, but it is quite easy to notice once you are aware of it, that is, I needed these entries to compute these entries, but these entries are not going to be used anywhere in future. So once I have computed the first column of L, I might as well throw these away. So an efficient way of storing it will be, do not allocate separate memory for storing this matrix L. You just overwrite these entries with these numbers. Similarly, these numbers will be required only to compute the first row of U. They will not be used in future throughout the algorithm. So, overwrite these numbers using the numbers that you compute. Then again, you come back to L and compute these things. For that, you will be using, other than whatever you have already computed, you will need these elements from A. Using them, you will compute these things. And again, once you have finished computing these elements of A will never be used in future. So you merely take this and write them here without wasting any additional memory. Similarly, you will compute this using these numbers and you just overwrite them. So when you use these to compute these and then you overwrite. And in this way, as the algorithm progresses, your entire matrix A will be split up into three parts. There will be a part, this part, which is storing the growing part of L. So this is L being developed. This part will be U being developed. So U is growing. And the remaining thing will store our original matrix A, the part that we have still not used. So this will store the original part of A. As the algorithm progresses, this L and U grows, and eventually this A will be completely overwritten by L and U. So using the same memory to store the original matrix A, you now have L and U. Of course, the original matrix is overwritten. If you need the original matrix also for some other purpose, you should better keep a backup copy of that. But if you do not need it, in that case, you can just store the entire thing in the same amount of memory space. There is another type of efficiency issue connected with this algorithm. When we did the Gauss-Jordan elimination, remember that we had to work with the augmented matrix. That is, both the coefficient matrix and the right-hand vector. When we worked with iterative methods like Gauss-Seidel or Gauss-Jacobi, there also the iterations involved both the coefficient matrix as well as the right-hand vector. Now, in many situations, it so happens that you have to work with many different systems, all sharing the same coefficient matrix but differing only in the right-hand vector. In that case, much of the work in Gauss-Jordan elimination or in iterative methods has to be replicated for different problems. But in case of LU decomposition, we are working with only the coefficient matrix. So you can do that as a pre-processing step once and for all. You split A as L times U. Now every time you are given some right-hand vector, then you will just carry out that forward and backward substitution separately. This LU decomposition will be computed once and for all. This improves the efficiency in situations where you have to solve the same, you have to solve many systems with the same coefficient matrix. As we have already noted, LU decomposition is far from unique even if it exists. We have already seen one way where this non-uniqueness enters into the picture. The way we took all the diagonal entries of U to be equal to 1 without loss of generality. You could as well take all of them equal to 2. You could take the first one equal to 1, the second one equal to 2, the third one equal to 3, like that. So it is far from unique. Now you might ask, why not take all the diagonal entries of L equal to 1? Yes, you might do that. Now these special decompositions have special names. If you are using all the diagonal entries of U equal to 1, then it becomes unique. As we saw, our algorithm gives unique answer if it does not get stuck. In that case, we call it Kraut's decomposition. If we put all the diagonal entries of L equal to 1, then we call that Doolittle decomposition. And if we put the condition that L will be transpose of U, in that case we call it Cholesky factorization. So Kraut, Doolittle and Cholesky. For Cholesky factorization, you also need the matrix A to be a non-negative definite matrix because you are splitting it as L times L transpose. Now, since one of the project already requires you to implement Kraut's decomposition, so I am not showing you the computer program to write down to implement Kraut's decomposition, but it is pretty easy. Okay, so that's all that I had to say about LU decomposition.